Hello physical science students, welcome to the next video on the equations of motion. This should be the last one in this series, and we're going to do projectile motion, which is probably the most complicated and difficult section that we have to do. Some of the understanding and concepts are take a little bit of wrestling, but once you understand it, it does make sense, and it does reward a little bit of perseverance in terms of the thinking. So let's try and work through it, and hopefully I won't confuse you too much, and away we go. Now, with projectile motion, this is what we call projectile motion, and we're only going to deal with situations where an object is thrown off or launched horizontally, so it has a horizontal velocity. If you do physics next year, we'll start doing situations where you throw it up at an angle, but we're not going to do that. In all our projectile motion questions, they're launched horizontally. And so classic examples, throwing something off a cliff, and so it's going to fall, but it's going to fall in this path, and we need to recognize that this path is a result of two motions. One motion is the vertical motion, the simple act of dropping, okay, and the other motion is the horizontal motion, and that's what results in it moving away from the cliff base and departing from the vertical motion. Now, if we had two balls here and they were identical, and one was launched with a horizontal velocity and the other one was just dropped, we need to also recognize that both the balls would hit the ground at the same time. So the time it takes for this ball to fall is the time it takes for this ball to do this pathway here. Now, for some people that just doesn't seem to make sense, but it's true, because both the objects are falling under the influence of gravity, and gravity only acts down. So gravity can only affect the vertical velocity of the object, and it can't affect the horizontal velocity. And that's why, if you did this as a little experiment, they would both hit the ground at the same time. So it also tells us that to analyze projectile motion questions, we're going to have to separate the horizontal and the vertical motion. And sometimes I'm going to be referring to horizontal velocity, sometimes I'll be referring to the vertical velocities, or the initial vertical velocity, or the initial horizontal velocity, things like that. And then we're also going to be referring to the velocity. Now, the velocity is what the actual velocity of the object is when it's moving. So that will be a combination of both the horizontal and the vertical. And you'll get the idea. We most commonly use that with the impact velocity, but we're also going to do a couple of other examples. So just to stress again, here we go. This object's being launched with this amount of horizontal velocity. So it falls this pathway due to the influence of gravity, and the horizontal velocity, because we ignore air resistance, again, that's something that's not the real world, but we do it just to simplify it, this horizontal velocity doesn't change, but the vertical velocity is increasing due to gravity. And if we had dropped an object, so this is the object, and if we had dropped it, okay, its velocity would correspond to the ones over here exactly the same. So the velocity would be increasing due to gravity. Okay, and we already hopefully know how to analyze that. What happens with projectile motion is students get confused between the horizontal and the vertical motion and bringing them together, splitting them apart and bringing them together. So we'll need to do a few examples. A couple more slides just to help explain. So again, here's a tennis ball. Notice that the displacement, this is like a time lapse, the displacement, the distance traveled for each time interval in the horizontal doesn't change, but in the vertical it gets more and more, so it's actually traveling further and further. It's getting faster and faster in the vertical. And here's our helicopter. This time it's not hovering, it's actually got a horizontal velocity, so the parcel that's dropped is going to be a distance corresponding to the horizontal velocity and the time it's taken to fall. So let's do a couple of examples, and there's all sorts of different variations in these types of questions, but you've got to sort of analyze them the same way. So what we have here, what will be the velocity of an arrow that is fired horizontally with a velocity of 90 meters per second 2 seconds into its motion? So that's a bit unusual. So what we're talking about here, here's the arrow. It's being fired. As time progresses, its vertical velocity increases, its horizontal velocity stays the same. Here they're using X and Y to differentiate between horizontal and vertical. That's an okay system. I don't use it simply because not all textbooks use it. And this line here would be what's called the velocity at that instant. And it's a combination of these two vectors, or these two velocities together. Okay, and so we need to know these two components, the vertical and the horizontal velocity, to work out the velocity at any of these instances. So let's say this is the 2 second one. So we already know the horizontal velocity, which is 90 meters per second, but we need to know this velocity here. So what we do is we look at it as if it's simply being dropped. Okay, because that's the motion that is the vertical motion. And from that we can know that if it was dropped, the initial velocity, not the initial horizontal, but the initial vertical, is 0. That's where students get confused. We know that the acceleration is due to gravity, and we're looking at 2 seconds. So knowing those three, there's our magic number, we can work out what are we after? We're after v. So we would then look at the equations of motion and work out that v equals u plus at is the equation we need to use. We do our calculations and we get v equals minus 19.6 meters per second to the minus 1. Now, of course, we were working in the vertical. That's our vertical velocity. Yep. So now we know these two velocities. We can combine them by bringing the horizontal velocity down to here, recognizing that this would be a right angle triangle and this would be the hypotenuse, because this is the one we were actually after, because the question asks us for the velocity. It doesn't ask us for the horizontal or the vertical, it wants the velocity, and that's what it's after. Okay, so this is redrawn over here. So what they've done here is they've done head to tail, it's called, where effectively this if we went back a diagram or back a slide, there's our object at 2 seconds, and it's got, that's a bit wonky, it's got its horizontal and it's got v vertical, and we've brought this one across to here, so it's a right angle triangle. Okay, and so we're now after the hypotenuse, and we also need to know this angle, which is the angle down from the horizontal, because that tells us whether the velocity is like this or like that or like this. So we need to know the angle. Let's get rid of that. Whoops. When you're ready. So they used Pythagoras. Hopefully we can all do Pythagoras to find the hypotenuse, and then they used trigonometry, in this case tan, to work out the angle. So you've got the velocity and the angle is down or below the horizon. So to fully describe v, you would have to say 92.1 meters per second at an angle of 12.3 degrees below or down from the horizon, or the horizontal. Okay, a lot of students forget about the angle, or they just put the angle but they don't tell us what the angle is relative to. So you have to be careful about that. Let's do another one. How much drop will an arrow launched at a target 120 meters away experience if it is fired horizontally at a velocity of 160 meters per second? So again, read the question 3 times, good practice. Even draw yourself a little diagram. So here's our archer at the Olympics, firing an arrow. There's our ground. The target is there. The arrow is going to go and it's going to drop a certain distance. Okay, and we're interested in that little distance there, which is a displacement in the vertical. So S vertical. Not to be confused with the displacement in that distance, which is actually S horizontal. Okay, and again, all this can confuse us. But as soon as we've got a motion which has a horizontal component and is falling, we know it's a projectile motion question. Okay, so let's have a look. Let's get rid of this. That's our diagram. And so there's our two pieces of information. Good practice, I recommend it. Divide your knowledge into the vertical and the horizontal. And in the vertical, you need U, V, A, S and T, and in the horizontal you need U, V, A, S and T, but because we're ignoring air resistance, we can say that A is 0, and we can say also that if we're given a U or a V, it's not going to change. So in this case it's 160 meters is the U and the final, so the initial and the final is the same because A equals 0. So here we can use our equations of motion because we actually got four things. And the other thing that we need to know or recognize is that the time it takes to fall or to travel this distance is the time it takes to fall. So the two times are the same. And so if we find 1t here, we can bring it across and use that t there. And that's what we're going to do. So we're going to find t in the horizontal. So we're only allowed to use these parameters in the horizontal. We can't mix the two up. Again, that's a common mistake. So we're going to use S equals ut plus half at squared. Put the numbers in and we get t equals 0.75 seconds. So that now, we can now use the vertical motion, this section, to find the vertical displacement, because this is what we're after. Okay, so we put the time in using the vertical, using exactly the same equation but different numbers. Again, don't mix up the vertical and the horizontal motion. So that's why it's a good idea to list them like this. Keep them separate and know where you're putting numbers as well. And so we get the displacement to be minus 2.8 meters. Alright, now let's do another question. In this case, a golf ball is thrown horizontally off a cliff at 20 meters per second and takes 4 seconds to reach the ground below, and then there's a whole list of things that we have to calculate. So, good idea to draw yourself a little diagram. There's our cliff. Let's put water there. There's our object. What do we know about it? Well, it's being thrown at 20 meters per second to the minus 1. It's going to go like that, and it's going to take 4 seconds to do that. And so it's also a good idea now, we're going to divide up our knowledge into vertical and horizontal. And so again, U, V, A, S, T, because that's exactly the same as dropping it. So we're imagining we're on a cliff and we're dropping it, and in the horizontal, U, V, A, S, T. Now, even before we do this question, there's a couple of things that we can put in. We would know that for dropping, the initial velocity is 0. We also know that the acceleration is going to be minus 9.8. Okay, and for the horizontal, okay, let's fill in the information that we know. We've got this one here, we've got this, and that's about it. But where does it go? Alright, so the 20 meters per second is the horizontal velocity, so that's going to go here. Okay, now, because the horizontal motion isn't being affected by air resistance or anything, the acceleration is 0. That means that the final velocity must be 20 meters per second to the minus 1. Got that? And we've got 4 seconds, so we can put 4 seconds in there because that's the horizontal time it takes. But we can also put 4 seconds in here because that's the vertical time it takes. Okay? Now we've got two S's. Make sure we don't miss those up. the horizontal is that distance there. Okay, the vertical S is how high the cliff is. Alright, so let's have a go at it. Let's go, what are we going to do first? A. Let's do the height of the cliff. That's what we're after. And so this is really asking us for S in the vertical. Okay, this one here. And so we can use S equals UT plus half AT squared. How did I know to use that one? Well, I looked at what we've got, and I looked at the equations of motion and worked out which one to use. So we're going to put our numbers in. There we go. And T equals 4. Don't forget the square. And then we're going to, because we've put in a minus there, it's going to get minus 78.4. That tells us that if this is our starting position, that's how far below it falls. So that's our height of the cliff. Done. That wasn't too hard. Now, B. What do we want? We want the, what's it? How far the ball will land from the base of the cliff. Now that's this one here. Okay, so that's the horizontal displacement. Bit slow writing. Now that, in terms of our things, unknowns, that's S horizontal. Okay, and again we're going to use the same equation, S equals UT plus half AT squared, because we've got this, we can put it in. Actually, well, there might be more than one way of doing this, but I'm going to use this equation. And so we go S, now U is 20 times by T, which is 4. Now because A is 0, this is all going to become 0. I'll just write it in there. So S becomes 80 meters. So that's how far from the cliff it went horizontally. Now lastly, C, which is the trickiest part, is the impact velocity. Now that's wanting the actual velocity, which will be a combination of the horizontal and the vertical velocities. So let's give ourselves a little bit of room here. So C is the impact velocity. Alright, impact velocity. Now we know that V horizontal is equal to 20 meters per second to the minus 1. That means that we need to find the vertical velocity, because we need to be able to combine the two to give us the final velocity, or the impact velocity. So if we look at the vertical, we've now got, we can actually put in some numbers. We've got, let's see, minus 78.4, and we've got 80. So we've now got lots of information, and we're just after this one here. So we can use, simplest one is V equals U plus AT in the vertical. Can't stress that too much. So can't mix up, do not mix up horizontal and vertical. U is 0. Whoops, let's just correct that. Okay, that was close. 0 plus, now this is going to be minus 9.8 times by T, which is 4. So there we're going to get minus 39.2 meters per second to the minus 1. So that's the final vertical velocity. So therefore, we now combine V vertical and V horizontal. And so if this is our water, there's our impact, and it might come in at this velocity here like this, and so we need to recognize that that's because it has this horizontal velocity and this vertical velocity. So that would be what we would call V, whereas these guys are our horizontal. So what do we got? Where's our horizontal velocity? That's going to be 20 meters per second to the minus 1. And this one is the one we've just worked out there, which is minus 39.2 meters per second to the minus 1. So we need to combine those two together, recognizing that we can bring this one down to here and give ourselves a nice right angle triangle. Okay, and so if I was to draw that triangle again, let's see, we'd have this and that. Let's get our blue back, recognizing that's that. And so we would recognize that to find V equals the square root of 39.2 squared plus, what's the other one, 20. So we're using what's that, Pythagoras? That's right, I nearly forgot. This is a long question, isn't it? But this is what we do. This is what we've built up to be able to do. So there's V. Now notice all the lines are working. I'm putting down so that if I make a mistake, whoops, which is just what I just did, I can go back and work out exactly what I have to do. So this should be 44 meters per second to the minus 1. So that's the actual impact velocity. No, because we need an angle as well. And we need to work out the angle. Now let's go green. And we want that angle there, down from the horizontal. Okay? So that angle there is actually that angle there. So in this triangle here, we want that angle there. So let's go, whoops, what happened there? So we would say tan theta equals, in this case, 39.2 divided by 20. Theta equals 63 degrees down from the horizontal or up from the horizontal, depending on what you want to say. And so our actual velocity, we would say, is V equals 44 meters per second. So this is the impact velocity, which is what it wants here. So the impact velocity is 44 meters per second to the minus 1 at 63 degrees down from the horizontal. Boy, that's a lot of work, isn't it? Okay, but usually in exams and things, you do these in parts, okay? And you just have to be systematic, alright? I look at that and it's so systematic. Makes sense to me. If you look at that and it doesn't make sense to you, rewind and watch it again. And if it doesn't make sense to you after that, rewind, watch it again, and if it doesn't make sense after that, come and ask me and I'll talk you through it again. Okay, because you've got to get your head around it. But we'll be doing some practice questions in class as well. Alright, oh, I need to get rid of that writing. So now you should be able to do the projectile motion questions. There'll be a couple of videos on the OneNote, and hopefully after exams we'll do some experiments, but we'll have to wait until after exams probably to do those. Okay, cheerio!